Okay, we got a wonderful experiment going here where all groups took solution A and solution B, measured out, as our instructions show us on the board, measured out 50 milliliters of solution A, put it in graduated cylinder A, and 50 milliliters of solution B, put it in graduated cylinder B. They poured the contents of A into B, and then they took a reading of what it said on their graduated cylinder. They poured 50 into 50. Group 1 came up with 99 milliliters. Group 2 also came up with 99 milliliters. So the question is here, we poured 50 milliliters into 50 milliliters. Why didn't it equal 100? Because even where I went to school in Tennessee, 50 plus 50 equals 100. And so the hypotheses now are the educated guess based on the vast knowledge of science that these men have. They're going to be able to tell us, at least in an educated guess, why this 50 plus 50 didn't equal 100. So who has the answer? All right, Alex, your hypotheses?
Solution A was more volatile, so it's going to evaporate more fast when you pour it into
Group 1, fast like fast.
It's a volatile solution. It's very volatile, so I mean it's going to evaporate really fast.
Very
And when
volatile.
Yeah, whenever we pour
Our
it.
hypothesis is based on the fact that
Oh, it would blow up quickly, right? Very volatile.
it's based on I spilled some on the
Volatile
table. It's
just
already
means it's
gone.
just evaporates really fast.
Evaporated upon pouring? Is that what you're
Yeah.
saying? Upon impact. Okay, so you're saying that essentially, solution A, 1 milliliter evaporated. Right? All right, that's your
Yeah, I mean-
hypothesis. And so you can think through this, right?
It's a liquid too, so I mean it's going to be sticky, so it's going to stick.
So why don't we
It
take
has a
another
vapor.
reading and see what we're at now?
You can smell the vapor, something that is evaporating.
And, okay, that's good logic. And so you're saying A. All right, so let me just give you something to think about whenever I go on to group number 2. You can change your hypothesis in a second. If it's evaporating at the rate of 1 milliliter per, I don't know how long it take you to measure it and pour it in there, 2 minutes or something like that. It should be empty pretty soon, right? There went 3 milliliters. So think about that. Think about that. If it's evaporating that quick, you know, maybe it's gone. All right, group number 2. What's your hypothesis?
Well, our original hypothesis was perhaps that the liquid fairy stole it.
The liquid fairy. All right, let's go to the second one then.
It's alcohol mixing with water, and therefore the alcohol evaporated.
Ah, okay. So you went a
Based on the
little,
mixture.
little step further, and you said alcohol mixed with water. So I think group 1 was getting at that, right? That one you deducted 1 was alcohol mixed with water, and so we see evaporation. Okay, what I want you to do is go back to the drawing board for just a minute or two, because I want to tell you that it's not evaporation. That's not what's happening. It's not evaporating that quickly. Water's evaporating. Alcohol is evaporating quicker than water. The smell that you see off the top of it, the volatility of the solution, it is evaporating quicker than water, but it's not evaporating that fast.
Is it one that's heavier than the other one, and it's going to kind of pull them down?
Oh, you're kind of on the right track, so just start thinking about that. John, let's leave Google out of it for right now. We'll bring them into it in just a minute. I know that's smart. That's smart. That's using your resources, but let your group think for just a few minutes on. Just a few minutes on.
Is there something
Critical
about the,
thinking.
is there something about the chemistry that like creates a bond that makes it smaller?
That's what I was
Yes, yes,
And
yes.
so
It's very simple. Whenever you break it down to what happens, it's very simple. It's not that complicated, though. You're along the right lines, but it's not that complicated even.
alcohol suspended in the water.
Explain that.
It's 2 different chemicals. I mean, it's like mixing oil and water. It's got, one's gonna be higher than the other one.
It does mix. I'll say it does mix.
Produces its
Does
effervescence.
one of them absorb the other one?
And then it stays.
Does it
Okay.
have to do anything?
It's not solid.
effervescing? Effervescing.
No.
Making bubbles?
It's nothing to do with making bubbles.
It is making
One of
bubbles.
them absorbs the other.
Kinda. Not exactly, but kinda. All right, let's think about soil. So I would use this little interest approach on a soil judging lesson or a soil evaluation lesson. So you think about soil. I don't know if this is fair to say, but at least on the Tennessee scorecard, the first thing that you had to determine about soil was pH. No, maybe your card's different, I guess. But if you're just gonna look at it, if you pick it up in your hand, yeah, first thing you determine about the soil is the texture. If you do the ribbon test, you did soil judging, you do the ribbon
Yeah.
test, it's gonna tell you how much sand, silt, or clay, essentially is in it based on how much of a thin ribbon you can make. And so you determine the texture based on soil particle size. What has the largest particle size?
Sand.
Sand, and the smallest is
Clay.
clay. Right, okay, well, this is the interest approach that I've used for that lesson, because what's happening here, and maybe I might get this backwards with fairly insignificant, whether I get it backwards or get it right, because this is what happens. These green bubbles represent the particles of water. Well, the particle size is so much smaller on the alcohol that it's able to do things like this. And it doesn't necessarily absorb it into the particles, but it's like if you took a 5-gallon bucket and you filled it full of baseballs, it's full of baseballs. But you can pour a bunch of marbles into it and they'd still go in there in the same space. And that's what's happening with what you're seeing here. And so it doesn't require the full 100 milliliters because the alcohol is falling down into those spaces. Now this didn't work as well, and I think it's because of our alcohol. We went and bumped some alcohol, and it was 70% isopropyl alcohol. And most of the rubbing alcohol that I see is 90%. And so whenever it's 90%, it'll usually measure somewhere around 97. So it gives you a little more of a drastic difference, so you know. I mean, they start thinking evaporation, you can say 3 milliliters, we'll just go on, you show how much 3 milliliters is. But really, it requires them to start thinking, and you don't tell them why you're doing this, you don't tell them why you're leading them through this little experiment. They're having fun, they're guessing, and you guys are adults, and you've had a lot of college education already, and so you know not to guess things that are pretty ridiculous that high school kids think could really be happening. It's all sorts of crazy stuff about chemical reactions that's happening and causing the loss of heat. We said that earlier. John Ward said, we see the loss of heat, and that does happen, in some situations, like the effervescent, is where you see it creates the bubbles and it creates the heat, and then it loses actually some of its volume. But anyhow, very simply, that's what's happening there. And so, I don't know, it's a little fun to do. It introduces the topic of soil particle size determination, and also it helps you to do a little activity that's more problem-based and not so much just, I've got a bunch of information to